Bom dia a todos, sejam todos bem-vindos à nossa aula inaugural desse semestre do PPGEE. Eu vou fazer agora uma pequena introdução em português e logo nós vamos mudar para o inglês, porque a apresentação do professor Pablo vai ser toda em inglês, certo? Então, agradeço a todos pela participação nessa aula inaugural. And now I will switch to English to introduce our speaker today, that is Professor Pablo García from the University of Oviedo. Professor Pablo took his master and PhD in electrical engineering from the University of Oviedo in Gijón, Spain, in 2001 and 2006, respectively. From 2002 to 2006, he was awarded with a fellowship from the National Research and Training Program by the Ministry of Science and Technology from Spain. He was a visiting scholar with the University of Wisconsin, Madison, USA in 2004, and the University of Nottingham, UK in 2013. He is currently a full professor with the Department of Electrical, Computer and Systems Engineering from the University of Oviedo. He is a member of the LEMUR Research Group, and his research interests include alternating current drive, sensorless control, AC machines diagnostics, and digital signal processing. He's currently focused on the control of grid-tied power converters for distributed resources integration, and particularly for the control of grid-tied battery energy storage systems. He is the co-author of more than 40 journal papers and more than 80 conference papers. He has been the principal investigator of more than 50 projects with companies, one European H2020 and 4 national funded projects. He is the co-founder of the Emphasis startup focused on the development of solutions for the integration of energy storage and collaborative self-consumption applications. He was a recipient of the 2005 IEEE Transactions on Industry Applications, the third place prize paper award, the 3 IAS Conference Prize Paper Awards in 2006, 10, and 16. And 1 EPE Conference Award in 2018. After the presentation of Professor Pablo, Professor Cassiano will chair the questions for the speaker. So, Professor Pablo, thank you very much for your kindness in giving us this inaugural class this semester. Thank you very much.
Okay, so thank you so much, Marco. Thank you also, Cassiano. Okay, so welcome all. And today I will bring in here some of the last experience that we had and we are having actually in our research group. This comes from a European project in which in our research group we are developing some of the power electronics solutions for the integration of energy storage in grid applications. And in particular, this project is very focused on a significant topic, which is how to decrease the cost of those solutions in order to have a widespread integration of these devices, okay? Well, in here you have my email contact, okay? So later on, if you want to send me any questions you might have, okay, just please feel free to contact me. Okay. So let me move the slides. Okay, so as Marco has said, I belong to the University of Oviedo, okay? The University of Oviedo is in Spain, north side. And from the University of Oviedo, the electrical engineering campus is not in Oviedo, it's in Gijón, which is a city nearby, just 25 kilometers apart. Okay, we are just on the coast. And within the electrical engineering department, I worked with the LEMUR Electrical Energy Research Group, okay? Myself and 2 other professors, we were the founders of the group, of the research group. We built it from scratch after finishing our PhD and some years of postdoc, okay? And the goal of the LEMUR is a research group that brings together expertise from 3 different areas, which are at the very end, which are power systems, power electronics, and control systems, okay? So basically, we have faculty from the 3 different knowledge areas, and also obviously students that they belong to the areas, with the focus at the very end to the idea that in order to bring innovative research in the let's say the electrical or the energy transition in a wide view, that we need to put together different people with different knowledge based, and that's why we created at the very end this group. Okay. So the group at the very end, these are a list of the research lines that we have, okay, that you can actually easily identify with a close relationship with the talk today, some of those, okay. So the first one is analysis and design of power converters topologies for energy storage, okay, and in which obviously I'm participating. And my CV and my previous education and my PhD, in fact, I belong to the control systems engineering, okay, even though always all the time since my PhD, I have applied the control knowledge to control of power converters or electrical machines, okay. So that's why I mean in this research line I'm involved together with some of my colleagues, okay. Also in the second one, which is dynamic analysis and control of power converters for distributed resources, I'm actually leading that research line. And from there, we are moving on, let's say, research lines that are at a higher level, at power system level, the power flow analysis for hybrid DC-AC grids, energy demand analysis and visualization, in which some of my colleagues, they have a very strong expertise, and in fact they have created also some spin-offs and so on. Modernization of the low voltage distribution network, also at the power systems. Electrical transportation, we have several projects, and some of the new faculties, they are working in that research line. We work in there in different aspects, from design of power trains, considering obviously not the mechanical part, just the electrical part, up to actually the impact of electrical transportation in the electrical grid, meaning, for example, not just how the electric cars, the impact they are going to have, but also in let's say, large transportation or massive transportation systems like electric trains, okay? And then finally, we have in our research group, we have a strong bias to technology transfer. So basically, we have a lot of collaboration with industry and with companies, okay? And that's why the last line is applications and industrial applications and knowledge transfer. The following one is, well, the Power Lab, okay? That is the one where the project I will comment is actually belongs to. So in there, we'll show you later on some other pictures, okay? But it's a microgrid with different low voltage microgrid, okay? In which we can actually quite easily change the configuration of the connected devices, okay? So that's a flexible architecture. It's highly focused on energy storage. We have, let's say, a significant amount of energy considering lithium-ion batteries, but also we have supercapacitors, and many of the publications and running PhD theses are actually focused on energy storage. And the last title, I don't know, is wrong, but it's not flexible in the sense that actually it's not just used by the researchers, but actually we let some externals from companies to use the equipment, the brand, for testing their own solutions. So moving next, this is my CV. Barco has already explained about it, so I will completely skip it, okay? So the agenda today is going to be, as I told you, regarding the sort of a specific task in the talent project, the one we are coordinating. That is at the very end, talent is for cost-effective solutions for energy storage integration. And in here, I will actually have a short description of the project and just go into a task we have done, which is the design of novel power electronic converters for the integration of energy storage at a scenario we have called the multi-home scenario. Okay, so the agenda is description of the project, introduction about the project, the scope of the project, the objectives, the implementation, how do we do it in our particular working packages, which are the research lines or tasks we are conducting, and the impact of the talent research. Okay. So it's I don't know how many of you know how the European funding works. I mean, they are 3 years project, okay, that they need to be run by a consortium, international consortium, typically from at least 3 countries in Europe, okay. We started in 2019, and because of the pandemic and so on, it was aimed to end last year, but at the very end, it's going to end this year, basically now. Okay, so it belongs to the H2020 call, okay, and the specific challenge and the technological development we are doing, okay, is at the very end power electronics for batteries and the software needed for the coordination and management of those batteries. And the scope of the project, it has to, at the very end, the impact is in the cost reduction, okay, so basically how to reduce the cost for these kind of systems to be connected and operated in the electrical grid. This is the consortium, okay, that we are people from Spain, people from France, Italy, people from Austria and Germany, okay, and we are in here. This is where Gijón is, basically in Spain, okay. So why is the motivation of the project? Well, you know, this is quite generic slide in which talking about how the electrical energy is used nowadays from the generation to the end consumer. So basically representing the losses in the different components at the very end of the system, okay? Moving to a system in which the generation actually can be moved as distributed generation. So those obviously mitigating transport losses, okay? This is where talent actually takes place. That is at the very end trying to, by the fact of renewable generation, you know, the intermittent generation of the PV or wind requires typically storage, but it's not just that. It's just that at the very end, it's not because of the intermittent generation. It's because the fact that was moving from large synchronous generator or power plants to distributed generation, the grid needs for extra flexibility, okay, and extra inertia at the very end, okay, that is going to be lost. And this is where the energy storage also needs to play an important role in that energy transition, okay? So in Talent, we will investigate, we were investigating, in fact, the use of energy storage at different levels, generation, distribution, and then consumer. Basically, this is where the technical or the works I'm going to explain later, okay, and the technical aspects, they are going to be focused more on this side, okay? So, a smart grid concept, okay, in which prosumers in mobility and industry with distributed generation, they change at the very end how the grid operates, basically because of how the protections need to work, lack of inertia, intermittent generation, and that at the very end needs to, the coordination of small units at the very end creates a huge challenge in the transition to this new, let's say, way of operating with energy. In the talent, the concepts we are applying, this is just already particular from the project, okay? We are doing scalable and modular power electronics topologies, okay? And the idea for the cost reduction is that those modular power electronic converters and topologies and controllers, okay? They can be reused, okay? So basically we are at the very end using the same design or with slight modifications for a variety of applications, okay? And that allows to, obviously, when you need to make those products or those power converters to the market, at the beginning, it's better to have less references which are compatible rather than have a wide scope of references that you need to manufacture each of those in a different process or with different materials at the very end, okay? We will use new power electronic devices, okay? In the talk today, in the things we have done, we started from a prototype, or a modular industrial prototype already, that was based on silicon MOSFET, okay? But also we have a third generation converter that is based on GaN devices. And in other partners of the projects, they were developing with silicon carbide devices. And then the last thing is the software at the very end that allows to manage the energy storage and to make the connection to the grid. And that software at the very end has to be very flexible in the sense that it needs to drive different assets from different manufacturers at the very end, and they have to be done with the minimum modifications in that software base, okay? So basically, again, the word is interoperable software. Moving ahead. So how the partners work, okay? Where we are. So basically, we are in here, okay? As I told you, we are in the multi-home scenario, okay? So at the terminal distribution, okay? We were participating both in the design of the power electronic converters and also in some of the control units in here in the project they are called Distributed Hybrid Energy Management System. That's the acronym meaning, okay? Then other partners like you see Gamesa and Mitsubishi, they work at district level, okay? Creating high voltage and high power converters. In here, Siemens Gamesa, okay? And Cybergrid is an Austrian company that they have the software for virtual power plants, okay? So at the very end, they coordinate actually all the control system with the different scenarios. So basically from here, they talk to the distributed hybrid energy management system at the different levels. And then at utility level, large PV plants or wind generation, we have the France CEA, okay, from France, that they develop a 3-level MPC up to 3,000 volts. So, idea of the project, the one I told you, okay, so we work in our case multi-home. The idea in here is that when you move down in the distribution grid, and again, we consider the impact of renewable generation, distributed one, energy storage is a must in there, okay? Because at the very end, you need to, it's not just for paying less for the electricity, it's just for security reasons at the very end, or for safety, in the possible contingencies you will have with renewable generation, okay? And that's a huge thing. What can you do? I mean, you can think about having energy storage, individual energy storage units at different houses or detached houses. That creates, obviously, the problem is getting worse and worse and worse because those multiple units at the very end, they should be coordinated, or if not, the grid is not going to work at all. And basically that creates a critical control problem. So basically, and obviously the cost of the individual units is typically larger, the cost of 10 small units rather than the cost of one medium-sized small unit. So basically, we use the multi-home scenario, okay, or concept in which we group together several of the distributed energy resources units, including storage, okay, that they serve to multiple users, okay, at the very end. Everything coordinated by the virtual power plant. So, which are we in this project, which were the targets? Basically, these were the efficient increase in 5% in our case, okay, and 30% cost reduction, okay? For that, we were developing power converters of this scale, okay, from 10 to 100 kilowatts kVA, okay? And for a voltage that from 400 to 800 DC, okay? This later on can be connected, obviously, with an inverter in there. We just work in the DC-DC. Okay, the inverter is a commercial one. This for multi-home. For district area, 1.5 kVA, 1 to 3 megawatts. Utility scale, 3 kVA, larger than 3 megawatts, okay? And these are the KPIs, okay, that we want to, at the very end, achieve at the different levels, okay? Again, basically we work, this is my presentation at the very end here, okay? The IBAT module that I will now let you know what it is, okay? And a multi-port power converter with these KPIs. So in here, in summary, the same thing than before, okay, with more text, so you have it as a reference, okay. So again, I will present more in here, okay. That is the bubble converter, and this concept in here, this is the IBAT, that at the very end is a modular battery with embedded power electronics, okay, that can be reused. This is the IBAT concept, can be reused for the different application levels, voltage levels. Regarding the software, I will not comment. I mean, we work also on that, okay, particularly obviously a lot in the control part, okay. This is the solution developed mainly by the partner CyberGrid at the very end. So how it works, we have a local controller using edge computing, that is the DHEMS, okay, and then those systems, those edge computers, they basically receive the references from the virtual power plant, and they distribute the references, active and reactive power mainly, to the different active resources connected downstream. Okay, that's the idea of the DHEMS. In our case, we just, develop our own, let's say, DHEMS for the multi-home, and we talk straight to the virtual power plant. That's everything we did in here, nothing else in the remaining points. Okay. Again, how everything works. This is the key factor for the software, okay? So interoperability, and more specifically, when you need to integrate assets from a variety of manufacturers, the protocols, they are typically different downstream. So basically, we need a layer in order to unify that, okay? And that goes to this cloud, is where the virtual power plant is, okay? And basically, we need this layer for making interoperability. What we did in here, in our case, I will comment later on, we work with a protocol from the IEEE, which is IEEE 1547, okay, that actually creates, is a protocol aimed for the integration of distributed generation and energy storage, and in particular for the implementation of some of the concepts about not grid forming, but just grid following, drop control, all the concepts that some of you probably know regarding the integration of power converters to the grid, okay? And that's on a standard, and this is how we did it in here. Working packages, I don't think that's much interesting. This is how we distribute the works, okay? So basically, we work in this working package, okay? And obviously, design and the validation. And now let's go to what we actually did in a more detail, okay? So basically, the idea is that the focus is to connect energy storage to the grid, okay? Basically, what happens when you need to scale these solutions, okay? I use this number because at least in Europe, this is a number that is typically for small scale house level, let's say, energy storage installations, okay? And basically, when you want to scale that system, in voltage, the problem is that the energy storage modules that you typically have for these applications, for this level, the voltage is typically 48 volts or 51 volts, depending on the number of cells, 15 or 16 connected in series, okay? When you want to make that to a grid connection through an inverter, for that size of energy, okay, and basically considering 1C or 0.5C, okay, the power in here is going to be in that range. That means that up to that range, actually up to 15 kilowatts in here, you go by single phase, okay, inverters. With single phase inverters, those inverters, they accept this small voltage with an internal DC-DC in order to boost and to be able to deliver the energy to the grid. However, when we increase that and we have a large requirement in the voltage, the solutions that typically the manufacturers they will do, and there are two kinds of solutions. First one is to have a dedicated different references, different modules for the different voltages. That for different manufacturers, they have a problem. Is that again they need to have prepared their product lines, okay, for different voltage levels or modules that they can be scale connected in series. That's the second option, of course. If you go to the first option, that's a larger module, that's expensive because of the cost production, okay? If you go to this strategy, the problem is that typically you are going to end up with more energy than needed, okay? Because it's quite difficult to design or to size a module for this application and for this application in series. It's not that simple, okay? Some manufacturers, they have But I mean, if they have that, you end up with a lot of modules in series. It's not the, let's say, the best solution, okay? So what we want to have is something like more flexible that allow us to, using the same kind of battery with obviously dedicated power electronics, to be able to move from a small scale to systems with a larger scale, okay? So that's the concept of the IBAT, okay, in which we embed together some of the power electronics with the pure energy modules, okay? In order to do that, nowadays, when we started the project, that solution, it was not existing in the market, okay? Nowadays, there are some very important manufacturers like Huawei, for example, that they are starting to do this kind of power electronics and putting in the market as commercial solutions, even though the characteristic of our converter or the converters we did in this project, they are slightly different and slightly superior. I'm not saying they are better from commercial purposes, I'm saying they are slightly different, okay? So this design, how we did it from the very beginning, the design should be able to work both in parallel and in series in the output, okay? And we should be able to use this reference design both for the connection of energy storage and PV generation. Okay, that was basically the specifications we had or we put to, ourselves in the design stage of the project. The concept for the how do we integrate this at the multi-home scenario is the one you have in here. Okay. That's the idea. The multi-home is, you need to imagine like a building, okay, in which there are obviously duals inside the building, and in which we embed energy storage and generation. Okay, this is a schematic representation. What we do is the following. At building level, we create or we put an interlinking converter, okay? That interlinking converter is just serving as an interface with the AC grid, okay? Obviously through the filter. It can be disconnected, okay? So the building breaker, it allows that the building works disconnected from the grid, okay? And inside the building, everything, this is obviously this is a 3-level MPC, okay? You have the plus, the medium point, and the negative rail, okay? And in here, what we have connected, okay, to either between the positive and the zero or the negative and the zero, we have a variety of converters, okay? That they could be the IBAT concept. This is the one I will spend more of the time in my presentation that allows to interconnect this battery. This can be also used for PV, okay, for interfacing the PV straight to the DC link. And then we have in here single-phase inverters, okay, which are at the very end a modular solution serving the loads to the internal duals, okay. Why all this power electronics? This is it has a very nice concept, okay. For example, it allows that doesn't matter how the loads are in here, that from the point of view of the grid, the building can behave always as a symmetrical load, okay, and you can be all the currents in here, they could be perfectly balanced. On top of that, okay, if for example some of those systems, those one inverter is actually is failing, okay, it's not disconnecting the complete system. It's just a dual, okay. The other remains operating completely normal, okay. And obviously it can be work completely isolated from the grid because we have internal generation and internal storage, okay. Those are basically the main ideas. How is the IBAT built? The IBAT idea built is built over this concept, okay? Something we call the IPEC concept, in which we implement together with the power electronics. This is a half bridge, okay, with the inductor already and the capacitor for the DC side, okay. We implement together the sensors needed for voltage and current, okay, and also an internal control system, okay, which is basically, it's not just the gate drivers and the responsible for switching the devices, but also the internal current control and voltage control, okay. And this is like an intelligent cell that can be one single cell, can actually, we have two kind of cells actually, half bridge or full bridge, okay. And then from those cells, they can be attached together, okay. And attaching those cells, we can build any kind, not any kind, but several kinds of power converters that we need, all of those bidirectional, okay, non-isolated up to this point, okay. And then this distributed control system is actually talking to the DHEM system that creates, let's say, the operating system, the operating control of the power converter of the multi-level, multi-home power converter, okay, the modular power converter. The IBAT prototype, the first one we designed, this is I will show you photos now, but this is the first design we did. These are the specifications, okay, for the module, the energy module, which is this one, okay. This was the first prototype we designed. Well, you can see it's a 3D for the power electronics, okay. The setup, it requires 2 IBATs connected in series. The IBAT output voltage rated one is 400 volts, and for multi-home, because it's 3-phase, we need 800 volts, okay, and it has integrated, as I told you, the power electronics and the control system. These are the specifications for the energy module. This is the aspect of one of the power converters, okay, one of the IBATs. This is the prototype. The prototype is basically the same size than the energy module. This is the silicon version. This is the second generation, okay. We did the design and we manufactured at the site of the university because, in fact, in the talent project, it was at the first thought to build 4 of these modules to generate. This is the module, as I told you, works 400 volts. It can be working with a certain margin in the output voltage up to down 375. And then if you put together 4 in series at 375, you achieve the 1500 volts. That is the one needed by the next partner in the consortium, okay? Because of the cost of this, what it happens with the cost of silicon, copper, and so on in the last years, we move away from this. This is working, and we tested pretty well. I will show you now. But we quit the idea of manufacturing 4 of those, and instead we moved to the 3rd generation prototype that is based on GaN devices, okay, that I will let you know also, okay. So this power converter, here you have it, in the lab, okay, with the units and the aspect with the scope, okay. And in here you have some of the tests we did, okay, in the system. This is one of the preliminary tests. We tested, this is almost 100 amps. We tested actually up to 280 amps, okay, even with better dynamics, okay. But this is one of the related tests. In here on the left, you can see these are the voltages from 2 of the units, okay, that they are operated in series in order to generate at the very end the 750 volts, okay, 375 times 2 volts. This link in the output of the 2 IBATs which are series connected. These are again the 2 modules connected for the series connection. For starting, well, these 2 cables, everything was very industrial except these 2 cables, okay. And these are the size of the module. You can see now how you can compare the size of the module. This is basically 40 centimeters. This would be around 60, 20, something like that, okay. And the module basically it's basically the same size than the power electronics than the module, than the energy module, okay. Obviously, this is not too commercial because you will say, okay, for each of the module, you will put this power converter, and this is not it cannot be sold, okay. Even though the idea is quite good, keep in mind that by the control system, what we did is that by serializing the power converters, each of the energy modules, they can simultaneously deliver different power, even though different power charging and discharging, even they can actually work one in charging and the other one in discharging. Okay, so it's a much nice. We use a modified group controller in the output for doing so. Okay, so it adds a lot of flexibility. Obviously, that bidirectionality of the 2 modules simultaneously, it allows, for example, to move energy from one to the other. Okay, in the case, for example, because of the state of health, one of those is actually with a lower charge than the other. Okay, and so basically we can do that by the control system. This is again some of the graphs we had before. Okay, with a little bit more detail. Okay, in here with again more currents, transients, and so on to illustrate. But this is the output voltage. Okay, with the 2 serialized. You can see here the transient behavior, which is is quite good. And the dynamics, and we push it actually more than this ramp, okay? And the dynamic behavior is quite good. What we did after, in order to avoid that large silicon version, we built a lithium galide prototype, okay? Is this one? This one, well, you can see the hand in here. This is the power stage, well, the power stage in here, okay? This is the side of the PCB with all the control system, okay? All the control system for the power electronics. The microcontroller is in this card. And this prototype in here is switching frequency from the previous one was 20 kilohertz. This one is 200 kilohertz. This one, this is a small card, is 7.5 kilowatts, okay? And actually, this is obviously the solution that is going to be industrialized. We built each of these prototypes, okay? And we are currently testing in our facilities, okay? And later on, it's going to be in here to France, okay, for making the testing at larger voltage. So the facilities that we have, we were making the testing. This is the photo I showed you before with the LEMUR, and this is the lab we built this part in here for this project, okay? In here you have the same photo. This is the interlinking converter in which we have two, in here we can actually emulate two buildings, okay? So we have two 3-level NPC with the corresponding AC filters, okay? And the systems, the DHEMS that we use for the control. In the roof, we have the PV, and this is just a general photo of the power converters that we have in the lab, okay? The structure of the microGrid where we are making the testing, okay? So basically, we are doing the testing after this feeder. This feeder is another interlinking converter with two AC feeders, okay? That in here allows to build, this is the building and the building, okay, in here. This is the control of the once you have the IBATs working, obviously we need to make the interface with the inverter, okay, with the grid, okay. So this is the control of the 3-level NPC power converter. The control of this inverter, as I told you, there was a switch for the disconnection to the grid, so we did it under two different concepts. Everything was done with a virtual synchronous generator control, and we are allowed to work in grid forming or actually grid following with a synchronous generator, a detail of the power converter and a figure with the transient behavior and typical figures from the AC side. This is in landing mode. Okay, this is in grid feeding mode with the transients, with the active and the reactive power transients, and in here the power from the battery. Okay, from the IBATs we have in the other side with a diesel link pass, as I told you before, 750 volts. Okay. And this is the what we are testing currently, okay, with the third generation IBAT prototypes that I told you they were modular with the GAN systems, okay. So basically they actually put together in an industrial chassis, okay, and those components actually they can be, I mean, the chassis allows to make a hot plug. Our cars they don't, okay, but we designed this in order to actually have a very modular system for the design of the IBAT, as I told you in the beginning, from 10 to 100 kilowatts, okay? So nowadays we have solutions that they allow to, the GAN solution 7.5 per power converter, okay? And basically we are going to do a parallelization of these units, okay, in order to be able with the same solution to arrive to the 100 kVA. The impact at the very end, okay, so basically we have measured the impact in the efficiency of the battery. You can say that it's quite difficult to understand that, okay, that efficiency cannot be better than the battery itself. It's true, but when you compare what happens with the battery, when you make a passive serialization of batteries in which the modules, they get actually with different state of charge because of the impedance that you have, the system, because of the active capability of moving energy between the modules, is able to achieve up to 10% more of use of the energy stored in the system, in the battery module, okay? And that's a huge benefit. And then the cost with the GAN systems, because of the GAN devices, sorry, because of the reduction in the magnetics, actually, they have a very, very, very nice cost for the cost of the energy storage system. So basically now the energy storage company that is going to commercialize the solution is actually making an industrialization of this system, okay? So we test the multi-home, now it's moving to district and utility, okay, in order to achieve actually that reduced cost of the batteries, okay? And basically that's all for my talk, okay? So I'm open to any question you might have. Okay, I can give you very much details about the power electronics. I just prefer to keep it at this level, and later in the questions, any question you might have, I'm open to it. Thank you.
Well, thank you very much, Pablo. Well, now we can start the questions and comments from the audience. So I invite everyone who wants to make questions to send it by the chat. And Professor Cassiano Heck will chair this session of questions. So, Professor Cassiano, I'd like to invite you to provide the questions and also to make your own questions to Pablo.
Okay, thank you, Professor Marco. First of all, I would like to thank you, Professor Pablo Garcia, for your great presentation about this important and up-to-date issue. Thank you so much. We have a first question from audience, from Álvaro Amorim. The question is on the screen. How did you deal with the saturation of the converters and inverters in this system?
The topology of the power converter inside, what we have in there is there are two kind of topologies for the silicon version. We have two stages. The first one is an interleaving three-phase stage, and after that, it follows a dual active bridge, but with a three-phase transformer. Okay, this is how it works. The topology in the case of the GaN solution, we get rid of the first stage and we actually go straight to a transformer. Okay, so to the three-phase transformer. In there with the magnetics so far, okay, we didn't have any problem with saturation. Well, just in the beginning. In the beginning, we had two iterations in the magnetics design. Okay. And we were experiencing some problems with saturation, particularly, obviously, in the utilization of the power converter due to the inrush current. Okay, and basically what we did, the problems were appearing in the three-phase transformer, and we will apply where I don't know if you know how the modulation schemes that you have in a power converter. So basically, you can actually play just with the phase shift, or also you can play with relative duty cycles, okay? And that second degree of freedom, it was very useful for avoiding saturation during the inrush current, because we were actually playing with small duties, generating like a ramp in the duty, okay? So the same voltage by the transformer was quite soft at the beginning, and in that way we avoid the saturation during the starting of the power converter, during the loading of this link and preparing the power converter. Other than that, we were not expecting any saturation problem in the power converter.
Okay, great. I have one question now, Professor Pablo. We were now facing an increasing interest on electric vehicles. And I would like to hear your opinion about the impact of these electric vehicles in this new future power system based on distributed energy resource. And also a second question, what do you think about the use of second life battery energy storage systems?
Okay, so regarding the first one, I mean, the impact is, is out of the question, I think. In the following, let's say, 10 years, just for having, room enough or time enough for the developing of the penetration in the market of the EV, it's going to be huge, okay? We have very close contacts to distribution companies in Spain, okay? And basically, they are trying, there are two kind of answers to that question. Some of the distribution companies, they are not worried about saying that the impact, the word in all of us talk about the huge impact in the distribution grid is going to be impossible to charge, to deal with the demand and so on. They are not worried because one of the companies, as very important in Spain, okay, they were not worried because the distribution grid was really oversized. I mean, talking about not just the transformers, but also the cabling, okay, of the terminal distribution grid. And they say that at this point they are not taking any, let's say, specific action for allowing for increasing the EV population. They were just worried in some of the cases, okay, that they were actually the ones I thought they were not important. That was they were in very large feeders that they are not in the typical in urban environment, but they are in rural areas in which the voltage fluctuation, because for just few electric vehicles, can be large. In there, what they are doing is basically preparing not the substation, but the transformation center, first the substation and the transformation centers, in order to accommodate for that extra load. The second answer is that those companies that they are worried, okay, and then in there also we have talks with that distribution company. And what they are now studying is flexibility. Okay, that is probably one of the goal words these days. In which at the very end, what they are studying is how to divide the distribution networks by different areas that they still have. Let's say in real time. This is not for planning, for operation. They have room at this time for charging and discharging, and all the EV chargers. They need to be they need to manage to set the maximum power they can load at each time. They can be changing in real time, and with that they try to make it to make sure that the stability of the grid is actually not compromised. That company in particular is also just looking from the other side, very much interested in exploring the vehicle to grid solutions, okay, in order to obviously use the batteries in the grid, the batteries in the vehicle for providing stability to the grid. They are raising some pilots in that direction. I mean, I'm not a big fan of vehicle to grid, at least at this point, just because of it's not going to be easy. How do you pay the owner of the vehicle for that service, okay? And the batteries, they are quite expensive. People that when you buy an electric vehicle at the very end, you are very worried about the range, you are very worried about the life of the battery, and leaving that, even though you are going to be paid, leaving that the battery used to the grid. Well, I don't know how it's going to work, okay? But I mean, they are exploring that for sure, okay? Regarding the second life of batteries, I mean, I think it's a huge market ahead. We have some contacts with at least two companies in Spain that they are developing the solution. I mean, and they are developing the solution actually talking with all the manufacturers. I mean, talking about Nissan, Ford, Renault. There's a large number of manufacturers, and actually using those batteries already, not just for a small scale energy storage, but for medium scale. Let's say, for example, the last project I'm aware of in this company, it was near 1 megawatt-hour. Okay, with batteries from EV. They do actually second life batteries. The problem obviously is that how you make sure that the batteries you extract and you put together in a system, they operate well together. There are two kind of techniques, okay? Some companies, they actually extract the module, and from the module, they actually extract the cells and they match the cells. Some other companies, they just match modules that basically they have the same life, okay? And it's I think the cost can easily, compared to the cost of the first battery used, it can easily go down by 25%, okay, in the cost. And obviously they have it's a technology to consider, I think.
Your mic is muted.
Okay, thank you, Professor Marco. Related to this issue, there is another question from Álvaro Amorim. He asks if the systems under analysis is able to work with second life batteries.
Yeah, I mean, for us, I mean, I learned some years ago when I bought the first battery for the research group. I was thinking, okay, a battery is a DC link, and then I can use it. Then later on, I learned it was not like that. Okay, it's more complicated than that. That's true. Okay, but I mean, considering the power converter, yes. The only thing is that from a second life battery, typically you need to operate it, let's say, with soft power profiles. Okay, this power converter has been designed as with 2C. That means double the power than the energy in the battery. For second life batteries, typically they operate at 1C. Okay, 1C, even, and some of those at 0.5C. That means that the power converter, yes, is going to work pretty well with second life batteries, but actually it's oversized because, I mean, you need that power range. Okay, so if you go down to quarter of power, okay, to see from 0.56 quarter of power, then you have some solutions that some, let's say, more classical power topologies that you can operate with. Okay, and it's much simpler actually.
Okay, I have another question. I would like to hear your concern about the safety aspects of the operation of the system. Are you worrying about fault operation of, for example, the batteries or the converters? Are you developing some strategy to deal with these issues?
Yeah, well, very good question. Thank you, Casiano. For the safety of the batteries, I mean, we did the following, okay? The batteries or the lithium-ion batteries at the very end, I mean, we need to look always at the chemistry, okay, which is the internal chemistry of those batteries. Nowadays, the chemistry, I don't know the percentage, but most of the people is using because of traction, because of Tesla actually, but still is LFP, okay? LFP chemistry, but that is the one we are using, is quite stable. Let's say, I mean, stable means in that system, in those systems, it means the following. It means that even if you make a short circuit, a clean short circuit over the cell is not going to burn. I mean, you will make smoke, but not fire. Okay, that makes a huge difference. And in the event a cell in a module, it gets fired, it cannot be propagated to the next cell. Okay, if you select other chemistries very popular in high performance traction, okay, which is, for example, MNC, that's a different thing, a very, very different thing. Okay, those cells, they are, I mean, we have experience created, let's say, small fires with that chemistry also. Okay, so MNC is a different thing. So basically, first of all, yes, for this application, the recommendation by everyone, is not me, is use LFP. Okay. Used typically in these applications, we were designing the power converter up to 2C because the manufacturers, they want to explore the power market. I mean, it's not energy, but it's a power application. This is because they wanted to have the application of, for example, participating in the high inertia market or in the fast frequency response market, okay? And then you require a fast response and power. But it's true that most of the battery manufacturers nowadays in these applications is an energy market, and basically they have modules operating at 0.5 or 1C. Okay, if you do that, the battery, I mean, is going to, or the cell at the very end is going to be basically pretty safe. Okay, and regarding for the power converters, no, I mean, we don't need any fault tolerant operation in this project. We have some previous publications together with Nottingham on fault-tolerant power converters, okay? In here, the only thing we did is that in the case of the internal single-phase inverters, okay, we, by design, even though one of the power converters inverters is working, we can actually disconnect it, okay, and it's not affecting the operation of the other. We tested with a short circuit, okay, in one of the single-phase converters, and that's the only thing. But I mean, we don't work in fault-tolerant. At the very end.
Okay, thank you, Professor Pablo. Unfortunately, we don't have more time for more questions. I believe if anyone has one question, he can send directly to Professor Pablo, yeah. I believe through email. Then I return to Professor Marco to finish our class here.
Okay, thank you very much, Professor Cassiano, and thank you, Professor Pablo, for your presentation. And I hope that our collaboration between our universities start to grow more and more from here to.
Happy to collaborate and to receive and to be there. Okay, so thank you very much for the invitation, of course. Okay, this is a pleasure for me. Okay, and hope that, I mean, some of the people attending, they can send some questions, and obviously to collaborate more between both institutions. I'm very happy to do so.
Just to let our students to know, but Professor Pablo right now is working with a former student from our university, that is Gleison Balen, is taking his PhD with Professor Pablo, and also other students went there some time ago. Caio Osório was one of our students that worked with Professor Pablo, so we have a very good collaboration between our groups. Okay, so we can finish right now. Thank you, professors, and thank you all the audience for watching and learning this inaugural class. So thank you very much, and have a nice day.
Thank you so much.
Thank you. Bye.
Bye.